So very first thing, let's quick do a recap of the last episode, intermolecular forces. You'll sometimes see this called van der Waals forces. We're just worrying about intermolecular forces, or the forces between molecules. By molecules, we're talking about covalent compounds or elements here. So we talked about 3 in the last time. The weakest we talked about were dispersion forces. Sometimes you'll see these called London dispersion forces or instantaneous dipole. How do you know if something, a particle, has dispersion forces? What is the only one requirement? It's covalent. Good. It must be a molecule. It must be a covalent molecule. So we're going to simplify this down as ionic compounds start with a metal or ammonium, NH4. So if it doesn't have any of those, it's covalent. It will have dispersion or instantaneous dipole. That is the weakest kind of intermolecular action we have. The next one in order of weakest to strongest is the dipole-dipole. What was the requirement for the dipole-dipole? The molecule must be what? Have opposite charges. So what do we call that when a molecule has opposite charges? Polar. Good. Molecule must be polar. Then the strongest one we had was what? Hydrogen. Good. Hydrogen bonding. Which was a kind of dipole-dipole, but what extra quality did it need? Good. It had to have hydrogen bonded directly to nitrogen, oxygen, or fluorine. One of those 3. And that is the strongest intermolecular action we have. These are between like molecules, so you're either looking at like one H2O molecule to another H2O molecule, or one H2O molecule to another molecule that can also hydrogen bond, like we did the example of ethanol could also hydrogen bond. So this is between like molecules. The next example that we did not get to is between non-like molecules. So on page 490, there's an example called ion-dipole molecule interactions. So that's between an ionic compound and something that is polar. So do we have this? So ion-dipole interactions. If you just take the name, ion-dipole, it means it's between something that is ionic and something dipole. What kind of things have dipoles? What kind of molecules? Polar. Good. So an ionic plus a polar compound. A great example of this is salt water. So I have sodium chloride, and I have water, H2O. Sodium chloride is ionic, water is polar. The way this works is the polar molecule, if we draw out water, so it's the bent shape, hydrogens are down. The oxygen end is partially what? Positive or negative? Partially negative. Good. It's more electronegative, so it becomes partially negative. And these hydrogens down here become partially what? Positive. Good. Now that sodium chloride comes along. When you put it in water, what do ionic compounds do when they dissolve in water? Chapter 4. When I put an ionic compound in water and it dissolves, does it stay a compound? No, it does what? If I put sodium chloride in water, would it stay a sodium chloride block? No, it does what? Dissolves, but it doesn't just dissolve. The sodium and chlorine are actually going to do what? Separate. Good. So they're going to break apart. We call that dissociation. It's going to dissociate, which means we're going to end up with sodium ions and chloride ions. So the sodium ions, positive or negative? Positive, good. And the chloride ions are? Negative here. So I have sodium ions and chloride ions. What's going to happen here is that the sodium ions that are positively charged are going to be attracted to what part? No, I didn't want to move just you. Move the whole thing. They're going to be attracted to what part of the water molecule? The oxygen. So they're going to move up here to the oxygen because that's negative and that's positive. Meanwhile, this chlorine here is going to move where? Down to the hydrogens where it's positively charged. And this is what allows small polar molecules such as water to dissolve ionic compounds because they literally help pull apart the ions. This is how it dissociates. It literally pulls it apart by drawing the positive ion to one end of the molecule and the negative ion to the other end. They literally rip apart the ionic compound. So this is an ion-dipole interaction. And this is why water is such a good solvent, because it can dissolve not just polar things, but also things that hydrogen bond, and it can dissolve a wide range of ionic compounds. Not all ionic compounds, as we saw in chapter 4 when we had our solubility tables, there were ionic compounds that did not dissolve, but a lot of them do dissolve. Any questions about those intermolecular reactions? Yes? Because those were all between like molecules, we're not really compared to that. This would probably be kind of weaker than a hydrogen bond because we're really not looking at holding molecules together. Technically, we're ripping apart a compound here, so it's not doing the same thing here. This is just explaining why on the like dissolves like world, an ionic compound can dissolve in a polar compound. All right, so once we can identify what the intermolecular interactions are and rank them from strongest to weakest, then we can start talking about the properties that is going to affect. So I'm going to switch over to the PowerPoint here just because they have better pictures of these. And we're going to talk about three particular intermolecular interaction properties that are related to the intermolecular interactions: surface tension, viscosity, and vapor pressure. And then we're going to do some calculations with vapor pressure today. So first of all, surface tension. We touched on this a little bit briefly last time. We were talking about how water molecules have those strong hydrogen bonds that hold the molecules together, kind of like they're holding hands. And that's why things like a paper clip can float on water, because here on the surface, it does not want to, here on the surface, it does not want to separate out. It wants to hold on. So in order to have something fall through the water, sink down, it has to break apart those hydrogen bonds. So the stronger the intermolecular interaction, then the higher the surface tension. So strong intermolecular forces have high surface tension. So things that can hydrogen bond would have a higher surface tension than something that can just dipole-dipole but not hydrogen bond. You're not going to need to calculate anything with that. This is just a concept. I would give you two examples of molecules and ask you which one would have higher surface tension. And you would just identify which one has the stronger intermolecular interactions. Surface tension also creates this new concept. This is the idea of capillary action we're going into. So here, we've all familiar with when we're measuring a volume in a graduated cylinder, the level of water here is not going to be flat. It does what? It becomes convex here. What do we call that? The meniscus. Good. So why does water do that instead of just becoming flat? And the idea has to do with surface tension and the idea of adhesion and cohesion. Because on the walls of this glass right here, so we've got glass here and water, glass is primarily sulfur or silicon dioxide, which is going to attract the water molecules because they are like molecules. It's also polar, so it's going to have the dipole-dipole interactions going on. And so the water molecules are going to be attracted to the glass molecules through the dipole-dipole interaction. At the same time, it's fighting, so it's getting attracted to the glass, but it's also fighting its own surface tension here that's trying to keep it holding together. So that fighting force between being attracted to the glass but also trying to hold together is going to cause it to end up with this convex shape. However, if I have something that is not like the glass, over here I have mercury. Mercury is a metal. It is not polar, it's a metal. So it's not going to have an attractive force to the glass walls. When this happens, it's going to actually repel from the glass walls, and you're going to end up with the meniscus here being pointing upwards. So that's the difference between whether or not you have something that is like interactions or repelling interactions in the glass tube. We call this when it starts to draw a liquid up a tube. So you'll see this a lot when you're drawing blood here. So if you're drawing blood, you touch that small capillary tube to the drop of blood. What does the blood do? So if you're drawing blood, you got a finger stick, you have a drop of blood in your finger, you touch the capillary to the drop of blood, what does it do? It sucks it up like a straw, but there's no pump in here that is pulling that blood upward. What's pulling it upward is something called capillary action. Capillary action is the fighting between adhesion and cohesion. So adhesion is between unlike molecules. So this, in this case, would be blood, which is mostly water. So this would be the water to the glass. Versus cohesion is between like molecules. So this is the water to the water. And what happens is that those two forces are fighting each other. It will draw itself out to the sides of the glass, and then it draws itself back in. And that's what kind of like a ladder pulls it up the tube of glass. So that is how capillary action works. And this is why it works with things that are similar to glass, on things that are polar, such as water. Capillary action would not work with something that is non-polar. So you wouldn't get capillary action if you were trying to draw oil, for example, up into a glass tube, because oil would not feel that adhesion force to the glass, because glass is going to be polar surface and the oil would be non-polar. Any questions about surface tension, adhesion, cohesion, capillary action? Again, these are just concepts. I'm not asking you to calculate anything for them. The next concept we're going to talk about is viscosity. So we're probably familiar with this term. What does it mean to you if I said a solution had a high viscosity? It's very thick, right? Something that's very viscous is very thick. So what's an example of something that you would find, say, in your kitchen that has a very high viscosity? Molasses, syrup, right? Honey, things that when you go to pour it out of the container, it does what? Pours fast or slow? Slow. It pours slow. So viscosity is a measure of the fluid's resistance to flow. So it's going to resist flowing. The higher the viscosity, the more it will resist flowing. So the higher the viscosity, again, picture if you had a container of molasses and you turn on its side, it's going to flow out it very slowly. Whereas if you did the exact same thing with, say, vinegar, it would just pour straight out much faster because vinegar has a lower viscosity. So the units for those are newtons times second per meter squared. But again, we're not going to calculate anything with this concept. This is just, I would give you two molecules and ask you which one would have the higher viscosity. The same concept applies as surface tension. The stronger intermolecular forces have higher viscosities. So something that could hydrogen bond would have higher viscosity than something that cannot hydrogen bond. So we don't really think about water as having a high viscosity, but if you compared it to something such as, say, gasoline that is nonpolar, it actually is higher viscosity than that. Questions about viscosity? Vapor pressure. We touched on vapor pressure briefly in chapter 10 when we were talking about the vapor pressure of water. So water is something called, it is an example of a liquid that is volatile. Volatile are compounds that can go into the gas phases at room temperature. So this is the example. If I spilled water on the floor and I just left it there all week, it would do what? Would it just stay on the floor all week? It would evaporate. Good. Because it's volatile. At no point here during the week would it ever reach 100 degrees Celsius or the boiling point of water. But it would still be able to go into the gas phase because it is volatile. This means that the molecules on the liquid surface, or the surface of that liquid, can escape out of the liquid phase, which is the condensed phase, into the spread out phase, which is the gas phase, without ever actually reaching the boiling point of that liquid. So when we were doing this in chapter 10, we had a table of vapor pressures compared to the temperatures. And as the temperature increased, the vapor pressure increased all the way up to the point where the vapor pressure at the boiling point was equal to atmospheric pressure, or the pressure of the room. And we had this example of, well, in places where you have lower pressure, atmospheric pressure, such as in the top of a high mountain, the boiling point was what? Higher or lower for water up there? Lower, much lower. So I think I had somebody look up what the boiling point was on the top of Mount Everest, and it was significantly lower than the boiling point here. So the boiling point, or the vapor pressure, is related to the ability of that liquid to escape into the gas phase. So here we've got some vapor pressure for a couple of different things. We've got water, diethyl ether. So diethyl ether was the example. I think I did dimethyl ether, but the same idea. Diethyl ether is polar. These are hydrogens coming off of the carbons. Because it has this oxygen here, it is polar, but can diethyl ether hydrogen bond? No, because these hydrogens, even though it has hydrogens and it's polar, why can't it hydrogen bond? Good. They're not attached to one of those three elements. They're not directly attached to oxygen, nitrogen, or fluorine. So diethyl ether has dipole-dipole interactions, but doesn't have hydrogen bonding, which means water has a stronger intermolecular interaction here. And as you see, when you look at these curves here, diethyl ether's vapor pressure here will increase at a lower temperature than water, which means diethyl ether will vaporize at a lower temperature than water will, because water has that stronger interaction that is holding the molecules together, meaning holding it in the condensed phase, in the liquid phase, so it's going to have a stronger force holding it there. So in this case, the stronger the intermolecular forces, the higher the temperature we're going to need in order to have that vapor pressure increase. And then here we have Mercury. Now, mercury, we didn't really talk about that because it's a metal. It doesn't have one of the intermolecular interactions because it's not a molecule, but it does have metallic bonds, so it's being held together by metallic bonds. Mercury doesn't like to go into the gas phase nearly as easily, but it is technically still volatile, which is why it's dangerous. So if we had a mercury spill, so we spilled mercury. Now, the old example of this was breaking a thermometer, but these days we very rarely use thermometers that actually contain mercury. And you're looking at the mercury line there. The reason why that's so dangerous is because that mercury will start to vaporize, to a small degree, and then you can inhale the mercury vapors. Is it a good idea to inhale mercury vapors? No, that's very bad for humans and for most life forms. We don't want to inhale mercury vapors, so that's why mercury spills are so dangerous here. So this is called the Clausius-Clapeyron equation. If you're in the textbook, this is on page 493, equation 11.1. And this relates the vapor pressure to the temperature here. So P here is the vapor pressure. And T here is the temperature. If you look at this, we can consider this like natural log of P, y, and then y equals mx plus b. What does that use to describe? Well, m is the slope, but it's used to describe a what? Slope-intercept line. It's used to describe a line, right? So m is the slope, x is the what? X, not the x-intercept, but the x variable, the independent variable here. And then b is the what? When you're drawing a line, the y-intercept. Good. So if I had a line like this, I have the y-axis, the x-axis. B is where it crosses the y-axis. The slope of this is m. All right, back to geometry. So this term here would be my m. The reciprocal of temperature, or 1 over temperature, would be my x, my independent variable. And then c is going to be my b, my y-intercept. Now what's r? Where have you seen r before? Chapter 10. What was r in chapter 10? It's a constant, right? The gas law constant. So that was the ideal gas law constant. And when we did this in chapter 10, we had a table of all the possible values of r depending on what our pressure was in units of. So we usually use pressure in units of atmosphere, so r was the 0.08206 liters per atmosphere over mole Kelvin. Here, though, our term up here is delta H of vaporization. What is delta H? Enthalpy. It's an energy term, right? What's our unit for energy? Kilojoules or joules, right? So we're going to need R, instead of being in units of a pressure here, we're going to need it in a unit of energy, which was on that table back in chapter 10. We just didn't really use it back then. All right, so let's go ahead and take this equation and boil it down to an equation we can actually use to compare temperatures at 2 different points to what the vapor pressures were at those 2 points. So we're going to derive this down. You're not going to have to worry about the derivation yourself here. We're moving on to page 494. I'm more interested in can you use the final equation. And so here is the final equation, equation 11.4, that you will be actually using this form of the Clausius-Clapeyron equation. And this is equation 11.4. The natural log of pressure 1 divided by pressure 2, so this is inside of the natural log, put parentheses there if you're not sure, is equal to delta H vaporization, so this is the enthalpy of vaporization, or how much energy does it take to vaporize that substance, divided by R, where R is the gas law constant, times the reciprocal of your second temperature minus the reciprocal of your first temperature. So R is the gas law constant. In terms of joules, instead of a term of pressure, the gas law constant is 8.314. and that is joules per mole Kelvin. So looking at that unit here, for R, that means that we need our delta H to be in what units? Joules, not per Kelvin, but joules per mole. So we need that in joules per mole. And we need these temperatures here, temperatures, to be in what unit? Kelvin. Good. Do you think I'm going to give it to you in Kelvin? No, what am I probably going to give it to you in? Celsius. So this equation, pretty straightforward as long as you can find the natural log button on your calculator. Natural log, not log log. So this is natural log base E, not log base 10. So you don't need to understand the trigonometry as long as you can find the log button on your calculator. You'll be fine. All right. For those of you who have not had trigonometry, real quick, if I have natural log of something, x, and I need to inverse this to get x out of that natural log, what is the inverse of natural log? E, lowercase e. So e raised to the x is the inverse of natural log. Why is that important? Well, if you're trying to get something out of natural log, you take the inverse. You just have to do it to what compared to the equation? Both sides. Good. So we're going to have to do that in the example we're about to do. Take the inverse of both sides. All right, let's try this out with an equation. Here. Go back to our diethyl ether example. The vapor pressure of diethyl ether is 401 millimeters of mercury at 18 degrees Celsius, and its molar heat of vaporization is 26 kilojoules per mole. Calculate its vapor pressure at 32 degrees Celsius. So molar heat of vaporization, that is your delta H, vape. So delta H vaporization is 26 kilojoules per mole. And then we have the two temperatures. So we said that we needed to convert those two temperatures to kelvins. So save time, we already have them both converted to Kelvin. Just add 273.15. But what is the other unit conversion we have to use before we can use that equation? Good. Change these kilojoules per mole to joules per mole, because we saw it said here, because R is in units of joules, we need delta H to be in units of joules. So how do you convert kilojoules to joules? What's the conversion factor? Times it by 1,000. Good. So there are 1,000. Kilo means 1,000. 1,000 joules per kilojoule. 1 kilojoule. So 26,000 joules per mole. Now comes the two schools of thought. You can either go ahead and plug in everything into your equation and solve for the unknown variable, or you can take the equation Clausius-Clapeyron and solve for the unknown variable first before you plug in the numbers. I usually fall into the second category. I like to solve for the variable before I plug in all the numbers in units. It just is easier for me when you're dealing with a larger equation like this. So again, that equation, the Clausius-Clapeyron equation, the natural log of pressure 1 divided by pressure 2 is equal to the molar heat of vaporization divided by R times 1 over the second temperature minus 1 over the first temperature. Which one of these terms am I solving for? Which one am I being asked for? The second pressure. It says calculate its pressure at 32 degrees Celsius. So we're being asked for the second pressure here. So P2. So I'm going to actually solve for P2 before I plug in any numbers. So the first problem is it is inside that natural log. So how do I get it out of the natural log? Inverse. Inverse of both sides. So inverse of natural log is lowercase e, and we're just going to have to do that to both sides. So e to the natural log, because these are inverses, they will cancel, and we'll just be left with P1 over P2 on this side. On the other side, it'll be e to all that big mess. Now I'm going to go ahead and open a fresh sheet of paper here. New slide. So I have room to work. Come on. Give me a pen. P1 over P2 is equal to E to all this. Delta H vaporization over R, 1 over T2 minus 1 over T1. Now, this whole thing, put it in parentheses or whatever you need, is inside of the exponent of E. That whole thing is. So I still don't have P2 by itself. To get P2 by itself, now I need to bring it to the other side. So it's being divided by, so to bring it to the other side, I'm going to have to multiply by it. And then take this whole term and divide it over here. So I end up with P1 divided by E to all that mess. Is all equal to P2. Now, at this point, we have solved for P2. How many of you guys love doing that kind of algebra? Just me? Okay, because some of us do. For those of you who don't, what is a great idea for your equation sheet that you're going to be able to use in your test? Have that down. Because now it is solved for the variable you need. All you have to do is plug in your numbers, making sure everything's in the right units. So if you don't like what we just did, just copy that down and use it, because you can use your equation sheet on the test. Now all we have to do is plug in all of our numbers. So pulling numbers from the problem, what was my initial pressure? P1. 401, good. So that's P1, millimeters of mercury. So P1, 401 millimeters of mercury, by E to the delta H vaporization, we converted that to joules, so that's now 26,000 joules. It does that sometimes. 1,000 joules per mole. Divided by R. R is the gas law constant, 8.314. Stop doing that. Joules per mole Kelvin. 1 over T2. So the second temperature, which was that higher temperature, 32 degrees Celsius, which we converted to Kelvin to be 305.15. Kelvin, minus their initial temperature, which was the 18 degrees Celsius, which we found in Kelvin to be 291.15 Kelvin. Whew. And remember, this whole thing is in those exponents, so when you're plugging this in a calculator, be careful with your parentheses. Don't close them too soon. So then, the fun part, plug all this into your calculator. By the way, to find the E function for most calculators, it is the secondary function of the ln natural log function. That's the lowercase e. I do. That should be a 1, not a 5. I don't know why. 1, 291, not 295. By the way, our temperature went up. So what do you think happened to the vapor pressure? Did it go up or down? Here, as our temperature increased for diethyl ether, what happened to the vapor pressure? To go up or down? It increased, right? This is a positive curve. So our number should go up, so we should end up with a number greater than 401. But not like huge. This isn't going to be like, you know, 1,000,000 millimeters of mercury. Should get up to some number still in the hundreds, but larger than 401. You want to? 656. Good. 656. Now units. Real quick. Millimeters of mercury. So here's joules cancels with joules. Moles cancels with moles. These two reciprocal kelvins are going to cancel with that kelvin. So the only unit we're left with is millimeters of mercury. All right. Is anybody not able to get that in their calculator? All right. So I could have also asked you to find a temperature for vapor pressure. So solve for one of the T's instead of solve for one of the P's. So one or the other. Either solve for one of the pressures as we just did or solve for one of the temperatures, which is of course easier because then you don't have to get in, rearrange it to solve for, get rid of the natural log. So that's the Clausius-Clapeyron equation. I feel like we can use that formula. Again, I recommend on your formula sheet having it both the original way and already solve for one of the pressures, especially if you don't like to do all that algebra on the fly. All right. Ready to move on? Talk about, so all of this so far was all talking about intermolecular interactions as it relates to things in what phase? Liquid. So now let's talk about solids. We actually haven't talked about solids at all. In Chem 151, we were never talking about solids. We were always talking about things either in the aqueous phase, so dissolved in water, or in the gas phase. We didn't really talk about solids because we don't really have chemical reactions that take place in the solid phase very often. But now we're going to talk about how we end up with those solids and what those structures are. So, first of all, we can have a solid end up as a crystalline structure. So crystalline structure has a very rigid, ordered, nice pattern to it, whereas compared to the opposite of this would be an amorphous solid, something that's just packed together in a random arrangement. There's no order to it. It's not very rigid. They're just all flowing around. So a crystalline structure, on the other hand, what we're going to focus on, has a repeating pattern to it. It's rigid. It's got nice order, very low chaos there. So we touched on this very briefly in way back in chapter 2 when we first talked about ionic compounds, and we said that they form large three-dimensional structures. And then we talked about that being a lattice, and we calculated the energy of that lattice back in chapter 8 when we calculated the lattice energy for ionic compounds. So when we talk about lattice structure, we're talking about that three-dimensional shape that either a metal or an ionic compound when it becomes a solid, or in some cases covalent compounds can even do this when they become a solid. So this depends on the particles involved, whether or not they're going to end up in a crystalline structure or in something that's more amorphous. So when we're talking about a repeating crystalline structure, and if you want to see these pictures in more detail, they're in section 11.3, starting on page 496 of the textbook here. The smallest repeating unit of the crystal is called a unit cell. So here is the simplest possible unit cell we have. It's just a cube. So we just have a cube, so we have the 8 atoms arranged to form a 6-sided cube. That is the simplest possible crystal structure we have. So if we take this repeat unit and just expand it out, we end up with this larger lattice structure, the whole thing all connected together. Each sphere here, of course, is representing an atom or molecule, and we're going to also call these things lattice points, where these bonds all connect here. Are going to be our lattice points. Some other shapes that we could end up with still from that simple crystal. Here, the simple cubic means all of these sides are equal. So this is a cube. All sides are equal. All faces are equal here. Tetragonal means that one side is going to be longer than another. Here. Rhombohedral means that we're not going to be all at right angles. So we've got a couple of different these. We're going to focus on this one first, simple cubic. In fact, the other shapes, although they're there, I'm not going to ask you to do anything with any of the other shapes. We're going to focus on the simple cubic because the math is a whole lot easier for that. We're getting a little bit into trigonometry here. So all sides are equal, all angles are right angles, 90 degrees. Nice and simple. Coordination number refers to how many atoms touch any given lattice point. So it's kind of like how many atoms are bonded to this atom. When you're forming this large three-dimensional structure, and we touched on this briefly in Chapter 2 when we first talked about ionic compounds, and for example, a sodium chloride structure, each sodium is not bonded to just one chlorine because it's going to feel attraction to every negative chlorine that's close enough to it to bond with. And that's how you end up with these large three-dimensional structures. So the coordination number is how many are close enough to actually form a bond with that particular atom. So the higher the coordination number, the more atoms can crowd around each lattice point, the more you're going to be able to pack into that. And that's going to affect density. Density. So the higher the coordination number, the more you can pack in. How do you think that's going to affect the density of that solid? Higher density. Good. So higher coordination number, higher density. It's going to be able to pack more in, pack more atoms in, means pack more mass in to the smaller volume, and that will increase density again. Remember way back from Chapter 1, density is the mass divided by the volume. So if we can pack more atoms in, that's going to increase the mass, which will increase our density. So again, the first one we're going to talk about is a simple cubic cell. We usually shorthand this SCC, simple cubic cell. Sometimes it's also called the primitive cubic cell, and that is just the 8 atoms forming that simple cube. Everything's right angles, all sides are equal. The other two that I want you to know, so these are the 3 kinds of cells I want you to be familiar with, are the body-centered cubic. So the body-centered cubic looks like the primitive cube with the addition of 1 atom in the center of its body. So I've just taken an atom and I've wedged it in between the center here. So that is the body-centered cubic, sometimes just called BCC, body-centered cubic. Face-centered cubic, starting with the primitive cube, instead of having one in the middle, we're going to put one on each face. Now, how many faces are there to a cube? 6. So we're going to add 6, these 6 atoms here, and then you can't see the one in the backs here. We're going to add those and stick them on the faces, kind of embed them in. So that's face-centered cubic, or FCC. When we start packing these here, we're going to end up with layers here. So here, we're going to look at the body-centered cubic. The second layer is going to be able to nestle in the grooves of the layer before it in the body-centered cubic, which is going to allow it to have a higher density. We're going to be able to pack these things closer in here. Yep. And these images are on page 497. So, although each lattice point here is going to be an atom, if we're just trying to figure out the density of this unit cell, we're going to have to consider the fact that each of those atoms is actually shared by multiple unit cells. So here we have a corner atom. So in our example of a simple cubic, here, to deal with my drawings here, simple cubic, got one back here. There, simple cubic. So this would be any of the corner atoms. Simple cubic only has corner atoms. The coordination number for this means that it is shared between 8 different unit cells. That's the coordination number for any of these corner lattice points, and a simple cubic number is 8. It's shared between 8 different cells. So that means if I'm looking just inside one here, just this little piece, what fractional amount of that atom is inside of the unit cell? If each corner atom is shared between 8 cells, each cell gets what fraction of it? 1/8. So each corner atom is only going to have 1/8 of its mass inside of any given unit cell. So just this little wedge here of the cube, or of the sphere, is going to be inside. For any corner atom, because it's being shared between 8 different cells, each cell is only going to have 1/8 of it inside of it. So just this little wedge here is going to end up being inside of any given unit cell. So if I'm trying to figure out the mass, this is what we're trying to build into. We're trying to figure out what the mass is inside of any given unit cell. It's only going to get 1/8 of the mass of any of those corner atoms, because each atom is being shared between 8 different unit cells. So that's for a corner atom. For a face-centered atom, here, let's start with the edge atom. Edge atoms are shared between 4 unit cells, so each of their masses are going to only have 1/4 of the mass inside. Edge atoms we don't really deal with in either simple-centered, body-centered, or face-centered, but we do have face-centered ones. In the face-centered cubic, we've got those atoms that are embedded on the face of each cube, and each of them are going to be divided between 2 different atoms, which means two different cells. Each cell has what fraction of the mass of a face-centered atom? Half. Good. And then, I don't think there's a slide for it, but the body-centered cube, the atom in the center of that body isn't shared with anybody, so its entire mass ends up. Take a simple cube and we're going to cut it to what is within the actual constraints of that cube. So in the simple cubic, we have those 8 lattice points. Each one of these atoms, what fraction of it is inside of the cube for the corners? 1/8. So each one of these has 1/8 of its mass. How many atoms do I have there? 8. 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 atoms. Each of them have 1/8 of their mass. So inside of the cube is the equivalent of what? 1 atom. This has the mass of 1 atom. The mass of 1 atom. I'm going to call this value Z, just because your textbook doesn't use this, but I use this because if you're looking at any sort of tutorials about finding the density of crystals, they usually use the term Z for it, so I don't want you to get confused. So I'm just going to use Z. So Z for a simple cubic centered, simple cubic cell is going to be 1. And this is the mass atom equivalency. Let's see. Simple cubic cell, SCC, the simple cubic cell. So there's just on the lattice points, nothing else there. Again, there's 3 kinds of cells I want you to know: the simple cubic, the body-centered, and the face-centered. Those are the 3 I want you to know. That has the mass of 1 atom. Let's skip over those images and get to this image. So here was our simple cubic. Z is going to be 1 atom. Here's our body-centered atom. So the body-centered cell here, we've still got those 8 lattice point atoms, but we also have 1 in the center. What would Z be for a body-centered? What would its mass be? All right, so I have 8 corners. Each of the corners has what fraction of its mass inside? 1/8, good. And then I have one more atom, that's the body atom. That's one right in the center. What fraction of that atom is inside? All of it. So what's Z going to be for the body-centered? 2, good. Z is going to be 2. So for a body-centered cubic, you have the equivalent of the mass of 2 atoms inside of the cell. Now last one, face-centered cubic. We still have those 8 corners. So Z for that is going to have the 8 corners times 1/8. But now instead of a body-centered, we have the face-centered ones. How many faces are on a cube? 6. So how many face-centered atoms do we have? 6. Now each one of those face centers, what fraction of that atom is inside of our cube? Half. So what is Z going to be for the face-centered? 4, good. So those are the 3 numbers you need. For a simple cubic, you need to know it has the mass equivalent of 1. For a face-centered, it has the mass equivalent of 2. And for, body-centered, it has the mass equivalence of 2. And face-centered, it has the equivalent of 4 atoms. Now down here, these calculations at the bottom here, that's the trigonometry behind finding the lengths of these. In the questions that I'm going to ask you, I'm going to go ahead and give you the side length. So you're not going to have to do the trigonometry unless you really want to. I'm going to go ahead and give you the side length. And these are all cubes, so all the sides are equal. Whether it's the simple cubic or the body-centered or the face-centered, all sides are equal. These are all cubes. We're going to simplify this down. All right. Yes? Mm-hmm. We're going to find the density of a metal using the idea of what crystalline structure it takes. So we're finding density. Let's jump into that. Let's look at this. Gold. Gold is a metal, right? Gold, most metals are going to crystallize into some repeating crystalline pattern. Gold happens to make a face-centered cubic unit cell. Now we can measure the density of gold. Pure gold has a density of 19.3 grams per cubic centimeters. We want to know what is the atomic radius of gold given that the density of gold is 19.3 grams per centimeter cubed. Ugh. So we are face-centered cubic. Let's go back to the picture right now and show you what part of this picture we're trying to find. So we're face-centered, this one. We want to know in this face what is the radius of any one of those atoms. So the very end here, again, you're not going to know all these equations, but this one would help. A is equal to the square root of 8 times r. So A is your side length. This is the edge length or side. R is your atomic radius. So we are going to calculate the side and use that in this equation to find what is the radius of that atom inside of the crystal. So outside. Yeah, it's outside. Yeah. All right, so I'm going to get a new slide. Give me some room here. And copy down what we know from the other side. It is face-centered cubic. Face-centered cubic, which means that Z is what? 4. We have the equivalent of 4 atoms. We know that the density, we were given that the density is 19.3 grams per cubic centimeter. We also know another piece of information. We know that it's gold. Now, in our density, we have the idea of mass there, grams. So what might be helpful to know about for gold? Atomic mass. So looking at the periodic table, gold, Au, what is its atomic mass? 196.96. Let me see what your textbook used. It just rounded to 197. We'll just round to 197 for 197. Now, symbol for molar mass is the curly uppercase M. Molar mass of gold is 197. What are the units for molar mass? Grams per mole. Good. Grams per mole. So we're going to make ourselves a formula. Now, if you're following along in the textbook on page 500, they kind of work this through a little bit more complicated than I would have. I'm going to actually make a formula that's going to take you straight to the value you're going to use, and you can use that formula on your formula sheet. I think that's a little bit easier. But the first time we're going to derive that formula. So, simplest equation, density is equal to what over what? Good, mass over volume. So, in the case of a cube, here we have a cube. What is the volume of cube equal to? It's our formula for the volume of a cube. Base times width times height. Now, in a cube, base, width, and height are all what? The same. So I'm going to call that the edge length or the side cubed. So S is our side length. So in our equation, I'm going to replace that V on the bottom with our side cubed, edge length cubed. M is the mass of that cell. All right, so we have in that cell, we have how many atoms? 4. So if we're doing just a simple equation, our number of atoms is equal to Z. Z is our number of atoms. Now, what is going to be the mass of 4 atoms related to its molar mass? See, this is molar mass is in grams per mole. So how are we going to relate moles and atoms? Avogadro's number. Good. Divide by Avogadro's number. So our mass here is going to be the molar mass times Z, how many atoms we actually have, divided by Avogadro's number. So let me show you how the units will work out there. So molar mass is in grams per mole. Z is in atoms, how many atoms you have. And Avogadro's number is going to be in the number of atoms per mole. So we're going to end up with moles canceling, atoms canceling, and we're just left with our mass in grams, which is what we want. So plug that in for M. Now here's this new equation. Density is equal to the molar mass times Z, the number of atoms, divided by Avogadro's number, and then you still have the side length cubed there. This is our equation relating the density to the side length and molar mass. I think your homework question actually asked you to find the density. Now the homework question, for those of you who remember from last year with Connect, I usually will tell you, okay, what is the density of copper given this information? Yes, you can Google what is the density of copper, and that will give you the correct answer on Connect. How much will that help you prepare for the test, though? It won't help you at all, because on the test day, you're not going to have Google. And for those of you even who took it online, I would usually take out the word copper and just say a mystery metal, so you can't even Google it. All right, so I'm going to take another sheet of paper here, as I like to spread out my work here. Keep it. New slide. No, I didn't want red, I want black. Density molar mass times Z over Avogadro's number times the side cubed. Now, in this case, which variable do I not know? Side. So again, as before, you can solve for the variable first, or you can plug your numbers first. Let's plug in our numbers first this time for fun. So the density of gold we were given to be 19.3 grams per centimeter cubed. Molar mass of gold was 197 grams per mole. Z, the number of atoms, because we were told that it was face-centered cubed, is 4 atoms. Avogadro's number, what is Avogadro's number? To the 23rd atoms per mole. And then the side cubed is what we're solving for here. Now, as far as units that cancel here. Change colors here. Grams are going to cancel. Atoms are going to cancel. Moles are going to cancel. And we're just going to be left over here with cubic centimeters. So bringing everything over to the other side, I ended up with 1.475 times 10 to the 22nd. Not cubic centimeters, but this is the reciprocal of cubic centimeters. And on this side, the only thing I'm left with is the side length cubed, but it's also the denominator. So what do we do when both things we want are in the denominator? Reciprocate. Reciprocal of both sides. So we did this in chapter 6 when we were finding the wavelength of the emitted from the hydrogen atom. Same thing here, reciprocal of both sides, which means 1 divided by both sides. So 1 divided by 1 over the side length cubed just becomes the side length cubed. 1 divided by this 1.475 times 10 to the 22nd becomes 6.779. I'm just keeping all the significant figures in my calculator. Times 10 to the negative 23rd. And now those centimeters cubed comes to the top. So if that's the volume or the side length cubed, how do we find just what the side is? What's the length of the side? Cube root. Good. So we're going to take the cube root of both sides. Cube root. We're running out of time here. Cube root. So cube root of that number gave me 4.08 times 10 to the negative 8th. And now cube root of centimeters cubed is just centimeters. And that's the side. Now we're going to plug in this one, which says the side length is equal to the square root of 8 times r. And solve for r. So 4.08 times 10 to the negative 8 centimeters divided by square root of 8 will give us r. (1.44 times 10 to the negative 8). We're still in centimeters. And the question did ask it for an angstroms. Angstroms are 1 times 10 to the negative 10 meters versus a centimeter is 1 times 10 to the negative 2 meters. No, I'm going kind of fast, but I know we're running out of time here. So to convert from centimeters to angstroms is a factor of 10 to the 6th. So we're going to just end up with 1.44 angstroms as our final answer.